Hey everyone, and welcome. I am absolutely thrilled to have you here for this explainer. Today we're exploring a seriously fascinating topic drawn straight from Unit 2 of the 7th grade physical science framework. We're going to completely unpack the principles of energy, how it transfers, and how it's stored. If you've ever looked at the world around you and wondered how things actually move, crash, change, or, even just sit still while holding an invisible charge, well, you're in exactly the right place. Okay, let's dive into this.
Here's our roadmap for today. First, energy systems and change. Second, kinetic versus potential energy. Third, storing energy in position in chemicals. Fourth, modeling energy transfer. Fifth, a big misconception about heat versus temperature. And finally, number 6, the exit question.
All right, part 1, energy systems and change. To really understand the physical sciences, we have to start by solving a massive, overarching mystery. When a system undergoes a change, whether that's two cars colliding, an ice cube melting in your glass of water, or a roller coaster flying down a track, where does that energy actually go? Now, what's really interesting about this slide is it gets right to the secret of the universe, according to the physical science standards. Energy is never truly lost. No way! It doesn't just vanish into thin air. Instead, it's constantly changing form or changing location. It moves from one object to another or from one state to another. And to track it, we need to know exactly what forms it takes.
Let's look at Section 2, Kinetic versus Potential Energy.
If we want to understand how these systems change and where that energy is, hiding or moving, we absolutely must break down the two main forms of energy that dictate physical science, and that's kinetic energy and potential energy. Think of these as two sides of the exact same coin. One is the energy of the active and the moving, while the other is the energy of the stored and the waiting. Every single physical interaction you witness is basically a dance between these two forms. So let's look at each one a bit closer.
According to the science standards, motion energy is properly called kinetic energy. It's directly proportional to the mass of the moving object, and here's the really fascinating part, it grows with the square of its speed. To visualize this, just imagine riding a bicycle at different speeds. The faster you pedal, your kinetic energy doesn't just increase a little bit, it increases exponentially. Because of that math, a car going 60 miles per hour literally has 4 times the destructive kinetic energy of a car going 30. Crazy, right? Or think about rolling different sizes of rocks down a hill. A massive boulder has way more kinetic energy than a tiny pebble moving at the exact same speed. Or, to use a classic example from the standards, imagine getting hit by a lightweight wiffle ball versus a heavy tennis ball. The mass and the speed dramatically change the kinetic energy you feel on impact.
Now, on the flip side, we have potential energy. This is stored energy contained within a system of objects. It isn't about how fast something is moving. It's entirely about the arrangement. It depends on the relative positions of objects interacting with each other or on the microscopic chemical arrangements of atoms. Basically, it's energy that is banked and just waiting to be unleashed.
Let's move to Section 3 and see how this builds. Storing energy, position, and chemicals.
We know potential energy is stored energy, but how exactly is it stored in the real world? Well, consider these specific, concrete examples drawn directly from the source material. First, a roller coaster cart. As it climbs higher and higher up a hill, it is literally storing gravitational potential energy based on its changing position relative to the Earth. Second, think about two magnets. When you push two repelling magnets closer together, changing their orientation, you're actively storing magnetic potential energy. Third, if you rub a balloon on your shirt and bring it near someone's hair, that static electrical charge is storing potential energy across that tiny little distance. And finally, on a scale we can't even see, chemical reactions involve atoms regrouping into new molecules. Some of those new chemical arrangements actually store energy right inside their bonds.
I want to read this direct quote from the science framework because it perfectly summarizes the concept. When the arrangement of objects interacting at a distance changes, different amounts of potential energy are stored in the system. Energy storage is incredibly dynamic. It's completely dependent on how these interacting objects are arranged, whether that's the Earth and a massive roller coaster or just two tiny atoms.
All right, Section 4, Modeling Energy Transfer.
Now that we've defined our kinetic and potential energy, we need a way to track how they behave. We're going to apply these definitions to model how energy actually flows through a system. So the crucial point is this fundamental law of the universe. The total change of energy in any system is always exactly equal to the total energy transferred into or out of the system. Basically, energy is conserved.
If the kinetic energy of an object changes, it means energy was transferred to it from somewhere else or transferred away from it to something else entirely.
We can visualize this using a really simple system model. First, you have a system input, where energy enters a defined space. Then, you have the energy transfer process itself. This is where objects interact. Maybe they collide, maybe they pull on each other with gravity, or maybe a chemical reaction occurs. During this process, kinetic and potential energy shift and change. Finally, you have the system output, where energy either leaves the system entirely or results in a completely new form of energy within that system. Tracking this flow is absolutely key to mastering physical science.
Moving on to Section 5, Misconception, Heat versus Temperature.
As we track energy flow, we inevitably run into thermal energy. And this brings us to a major stumbling block. In everyday language, we throw around words without really thinking about their strict scientific definitions, and that causes huge misunderstandings. So I want to pose this question directly to you right now. Is temperature the exact same thing as total thermal energy? Think about a cup of boiling water and a massive iceberg. If you use a thermometer, the boiling water obviously has a much higher temperature. But does it have more total thermal energy than an entire iceberg?
And this brilliantly illustrates the distinction. Temperature is simply a measure of the average kinetic energy of the particles in a substance. It's just an average. But total thermal energy is much broader. It depends on the temperature, yes, but it also depends on the total number of atoms in the system and the state of the material. Because an iceberg has trillions upon trillions more atoms than a small cup of boiling water, the iceberg actually contains far more total thermal energy, even though its average temperature is way lower.
This naturally leads to how we define heat. In everyday life, we say things like, close the door, you're letting the cold in. But scientifically speaking, cold doesn't move. In science, the word heat is used very specifically. It refers only to the energy that is transferred due to a temperature difference between two objects. Energy spontaneously transfers out of hotter regions and into colder ones. So you aren't letting the cold in, you are actually letting the heat out.
And finally, Section 6, the exit question.
We've covered a tremendous amount of ground today, from the invisible bonds of potential energy to the massive kinetic impacts of moving objects. And we've modeled how all that energy flows and transfers. Now, I want to leave you with this final provocative thought. Take a look around your room right now. Pick one object. Maybe it's a ceiling fan, a battery on your desk, or a book resting high up on a shelf. Based on its motion, its relative position, or its chemical arrangement, what is the evidence of its kinetic or potential energy? Where did that energy come from? And where is it going to go next? Think about it, and you'll realize you're surrounded by energy systems constantly waiting to change. Thank you so much for joining me for this explainer, and keep questioning the world around you.